Hello, my name is Audrey Mariani, and this is my Projectile Motion Lab video. To start off, I want to go a brief overview of what we did in our lab. We used a whiteboard eraser marker as an object, and we measured its position and its velocity and the forces acting on it through a projectile motion. We wanted to create and compare a computational model of projectile motion with a model from a lab experiment using GlowScript technology and the Tracker app. We observed and recorded the motion of the object as it is thrown. The principles that we used in this experiment were the position update formula, velocity update formula, gravity, and drag, all of these which can be derived from the momentum principle and the Newton's second law, F equals ma. The experiment, as I just went over, it was just us throwing a whiteboard eraser, and we used meter stick as the calibration marker so that we could accurately measure everything. Here's our data from it. As you can see, our graphs look quite different between the computational model and the real model. The experimental model being the one in the upper left and the computational models being the one on the right and the bottom. The thing that is important to note is in our experimental model, our object was thrown in the negative x direction, which is why a lot of our values have the opposite sign. Oh, shit, you're Our velocity update that we used, we did have to take into account that we had an initial velocity since my arm was moving and that's what threw the eraser. But so we were able to calculate that using the Tracker app and the velocity formula, and then from there we were also able to calculate the final velocities in both the x and y direction. Here is our code that we used for the experiment. As you can see, we have the initial position and velocity vectors in lines 49 and 50. We have the drag proportionality constant in line 63. That was used to calculate the overall drag force on the object throughout its motion. Then in lines 79, 80, and 81, we have the total magnitude of the forces acting on the object. In 84 and 85, we have the momentum principle, which allows us to update the velocity and the position throughout. And then in lines 104 through 109, we have the arrows representing forces in the model. Here you can see the drag versus no drag, velocity, position, and in position x and the y direction graphs. As you can see, there is definitely a major difference because when there is drag, things are no longer linear because there's an external force being acted on it, even in the x direction. That's why we have that over arch there rather than the flat linear line in the no drag section. Here we have our experimental data versus our computational data with no drag. As you can see, the lines are definitely very different, but once again, you have to take into account that in our experimental data, it's negative values because it was traveling in the negative x direction. However, the y and the t should still be relatively accurate. It's just the x that is affected by this. And you can see that slight curve in the experimental that matches almost the no drag, or a little bit, and then the other two lines, which are both linear. But here you can kind of get a little bit more of an accurate feel for it because as you can see, the x has a slight bend to it. It's not exactly linear, which is what you see with the computational model. Once again, it would be flipped, and the y still has that curved shape to it. Do any of our models predict a terminal velocity? No, they do not predict a terminal velocity because the drag force is at no point equal to the gravitational force. This is demonstrated in these graphs because at no point is the velocity, the graph of velocity in the y direction flat. So it always has a curve, meaning it always has a non-constant slope. And if the object, and to answer another question, if the object were initially thrown straight up with the same initial speed as it was in our experiment, would it take the same amount of time, longer or shorter than it did in our experiment? And our answer was that it would take longer because it would be going to a higher point, since it would no longer be needing to multiply by sine theta. It would just be multiplied by 1, which means that the value would be at its maximum and it would be going as high as it can, which gives it more time in the air, which lengthens the time that it's not off the ground. In conclusion, the object that we measured moves like a projectile and has constant force related on it, one of it being drag force. Thank you.